Hi everyone, and welcome to Cooking Serverless Recipes with Azure Functions and Azure Cosmos DB. Let's start by defining what serverless actually is. It is an evolution of the cloud paradigm. Most of you might be familiar with terms like IaaS or infrastructure as a service, or the use of virtualized environments or virtual machines that runs in the cloud where you have complete control and responsibility over the OS and the software running on each instance. PaaS or Platform as a Service that allows developers and companies to run and manage applications without the complexity of building and maintaining the infrastructure behind them. In the recent years, there has been an extension of PaaS called FaaS or Function as a Service, a term most commonly related to serverless computer microservices architectures, where the developer focuses on creating small pieces of code that execute based on events without the need to worry about any kind of platform running behind. This evolution can be summed up into three main points. It is a fully managed service, meaning that the OS and framework patching is performed for you. There is zero administrative tasks and no need to manage any infrastructure at all. You just deploy your code and it runs within seconds for short periods of time. It scales quickly and vastly within seconds. You don't need to configure any kind of scaling logic. It scales to match any given workloads, from 0 to handle tens of thousands concurrent functions invocations within seconds, and you pay only for the time your code is running. And finally, it reacts to events coming from Azure or other third-party services in almost real time. From a business point of view, this means that you can manage apps, not servers, and you can focus on your app logic. If you're an insurance company, for example, you want to be spending your time on providing a great customer experience and maybe optimizing the claims approval process. You don't want to worry about servers. You have a reduced DevOps cycle. Since you are no longer required to worry about scale and availability, your effort towards non-core activities goes down significantly. Serverless architecture leads down to something we call a pit of success, by providing a model where components are small and decoupled by design, thereby reducing integration challenges. Finally, you have a faster time to market. The time you saved leads to faster app building. Serverless also provides an easy and cheap way to do experimentation, thereby allowing for faster iterations and prototypes. Now let's talk about Azure. Azure Functions is Microsoft's serverless platform, which enables customers to respond to events through code that in turn processes data that could be coming from or headed to any number of services. With Azure Functions, customers have the ability to build, test, and debug their functions code locally on their own machines before the code is even deployed to the cloud, with tools like Visual Studio, Visual Studio Code, and even a multi-platform command line tooling. Secondly, Azure Functions include unique features like triggers and bindings that make it super easy to set up event-driven architectures and simplify communication with data sources. It supports a number of programming languages, from C# and Node.js to F#, Python, and even Bash. Lastly, functions support concepts such as continuous deployment, which makes it super easy to integrate them into any existing DevOps pipeline. At Azure Cosmos DB, we are committed to be the geographically distributed database for the serverless era, so we work closely with Azure Functions to create meaningful integrations that would enable customers to react and interact with the data inside their Cosmos DB containers, with little to no effort and following best code practices. After this brief introduction, you might be wondering, what does anything have to do with cooking? Well, when you cook, you often use recipes, which are step-by-step instructions that, using some ingredients, yield an expected result in the form of, well, food. In our case, we'll go through some easy recipes that cover the most common scenarios of using Cosmos DB with functions, including code samples and required ingredients in the form of bindings and triggers. Let's start with the input binding. It will allow you to retrieve one or more documents from your Cosmos DB container using an ID for a single document or a query for multiple documents when the function is triggered by an event, for example, an HTTP call, a message in a queue, a schedule, or a call from any other external services. The interesting part is that you can dynamically bind information from the trigger to the input binding. For example, you can pick attributes from your queue message or HTTP request and use them within the query, or match a certain data to the ID you want to query. The result or results will be available inside the function as an input parameter. The beauty of this is that you don't have to worry about maintaining the connection to your Cosmos DB account. It is taken care for you in a performant way behind the scenes. When I say in a performant way, I mean that the binding will reuse existing connections in between executions to avoid socket issues, especially useful for scenarios with thousands of executions as it reduces any cold start time in the connection initialization. Now let's see the input binding in action. I'm going to start with a live Cosmos DB account that has two documents, both with the name and city properties defined. Both are shown from different cities. And then I'm going to use Visual Studio Code as my tool to run the function locally. It can also run in Windows, Linux, and Mac. The function will have an HTTP trigger to start the function and receive some data, and then the Cosmos DB input binding to query that data by ID. The binding takes a database name, collection name, and connection string for the collection we want to query. And in this case, I'm going to use the ID property. What is going to happen is that the HTTP trigger is going to send some JSON payload. It's going to deserialize it and dynamically bind the query.id property from the payload to the ID attribute of the binding. The binding will use the internal Cosmos DB client to query the collection for a document with that particular ID and return it as a variable inside the function. All the code being used in this and the other demos will be available at the end of the session. I will now simulate a test payload using Postman. You can see that the body is a JSON document that includes a query attribute and an ID property. When the query runs, it will pull the document and return it on the response. We can now send the test request, and we'll see in the response that we have a full document that's coming from our live Cosmos DB account. You could see that I was not creating or maintaining any kind of Cosmos DB client or connection. The binding was taking care of everything for me. Our second demo for the input binding does a similar thing, but instead is using the root attribute of the HTTP trigger to bind the particular root attribute, in this case an ID, to the ID attribute of the Cosmos DB input binding. Now going back to Postman, you can see that I'm calling the function using the root without passing any kind of body parameters, and the response contains the document from the live Cosmos DB account. Now going to my last input binding sample, the next one is going to use a custom query to actually find more than one document. As we can see, again, we are using the HTTP trigger as the input. It could be a queue on a message or any other input mechanism to actually bind a custom class. In this case, it's called query. It has two attributes, one name and the other city. So when the body of the request comes into the function, it will be deserialized into that class, and we are going to bind from that class both attributes inside a SQL query that's going to be run into the Cosmos DB instance. You can see that I'm going to select all documents where the name and the city matches the values coming in the query. And in the body of the function, we are now returning a list or an enumerable of documents instead of a single one. Now going back to Postman, I'm going to send the query, filtering by Sean and Las Vegas, to the function. And one of the things that I did is I added a breakpoint in the function. So that's one of the things that you can do when you're working locally with any kind of tooling, either Visual Studio Code or Visual Studio, and you can inspect different variables. In this case, I can see that the query returned one document, and I can keep going over the steps and over the code, or just run it and continue until the end. The next integration available is called the output binding. Acting in a similar fashion as the input binding, it allows you to easily persist one or more documents to a destination collection by using an output variable inside your function. Similar to the input binding, the connection is maintained for you behind the scenes to optimize high load scenarios. You just need to focus on sending the desired documents to the output variable. Now I'm going to use for this output binding demo the HTTP trigger again as my starting point, and the Cosmos DB output binding. You can see that in this case the HTTP trigger has a my class as the class of the input. That means that the HTTP trigger is going to deserialize the body of the request that is coming into this class and then pass it along as a variable inside the function. Now getting to save this document into the Cosmos DB collection is pretty simple. You just have to assign the out variable to the input single document variable in our function, and that's pretty much it. Now going back to Postman, I can now call this HTTP trigger, passing a new object with the name of John but in the city of Buenos Aires. And what is going to happen is that this new object is going to be stored in our live Cosmos DB account. I can now refresh my collection in the portal and see that I have a new object with the name John and city Buenos Aires that has been stored by the Cosmos DB output binding. Now for my last output binding sample, I'm going to use the HTTP trigger, but instead bind it to an array of objects of my class instances and use the async collector. That's a feature available in the Cosmos DB output binding that will allow me to store more than one document in a single function execution. You can see that within the function's code, I'm iterating over the input documents, then calling the addAsync method on each of them, effectively storing every document within the Cosmos DB collection. Now going back to Postman, I'm going to call this function by sending an array of documents. In this case, there are two documents, both with ID, name, and city. I'm going to change their names from John to Mark. I'm going to send them to the function. I'm hitting the breakpoint and I can see that the function is receiving both documents. And then stepping into the for each block, I can see that I'm iterating over both documents and both are being sent to the addAsync method. Now going back to the portal, I can see once again, refreshing my collection, that both marks are now stored in the collection through the function's output binding. Now, these two integrations are meant to make your life easier by handling all the background operations for you. But there are scenarios where you might want to have more control and maintain your own customized client connection to interact with your Cosmos DB account. Before we dive into that scenario, we need to understand how function apps and functions work with instances. Functions exist within a function app, which acts as a logical container. You can choose to work in an app service mode, where the function app is managed by you in the form of an Azure App Service, and you can control the scaling based on your needs. Or in a consumption plan, where you really don't care about maintaining any instances, you just want your functions to execute, and if they need to scale up more instances to process the amount of work, it is handled by you automatically. Within an instance, you will define the code you want your function to run, and this code will be executed every time the function is triggered. It could be once a day or 100 times per second. It is important to understand this in terms of memory and variable management. Any locally declared variable within a function's run code will be initialized in each execution. Any static declared variable will be initialized once and reused in each execution. So what's the difference? When your variable is a database or a service connection or any HTTP-based client using a local variable, means that the sockets and connections are open and established for each execution, which might be okay if your function runs once an hour. But if it runs hundreds of times a second, this will lead to socket exhaustion and memory peak scenarios. So, the best practice when working with any service or HTTP-based client connection is to maintain it as a static variable or use lazy patterns that ensure that the variable is only initialized once and reused among all executions within the instance. It is important to understand also that static variables are not shared among instances. Basically, when your function app instance scales up, it affects all the included functions. Each instance manages its own memory separate from other instances. So let me show you the effect of a static client in existing function. In this case, it's an HTTP trigger function that has an internal private static variable called client. In this case, it's receiving an array of documents very similar to the output binding sample that we've seen before, and it's going to store these documents within the Cosmos DB collection. But in this case, this getCustomClient function is going to create a customized document client that's changing the retry options and the preferred locations. In your case, you can customize the client for your needs, but the idea is that this getCustomClient function is going to be called just once on the first call to the HTTP trigger function, and then reuse in subsequent requests. In Postman, I'm going to call the function by sending an array of new documents. In this case, the IDs are static1 and static2 and named Julie. And when I send it, you can see that the breakpoint is hitting the creation of the custom document client. And then I'm going to go back to the Azure portal and verify that these two new documents are in the collection. I can see them, both Julie's, in the document list. Then I'll go back to Postman and change the ID of the documents. Let's call them static3 and static4 and call the function yet again. But this time the breakpoint is not being hit. That's because the static client has already been initialized. We can now go back to the Azure portal and refresh the documents once again and see that in this case static3 and static4 has been created. That's the main point of using static variables, is that you maintain a single copy of it across all executions of your function. The last of these integrations is called the Cosmos DB trigger. It's a way for you to trigger code based on the activity on a given collection in your Cosmos DB account and process or work with these changes. The trigger receives batches of inserted or modified documents that you can work with and, as we mentioned earlier, interact with any other service. For example, triggering a notification or a call to an API when a document is inserted or modified, stream processing for IoT or performing analytics, additional data movement by synchronizing with the cache search engine or data warehouse, or archiving data to cold storage. Let's see the trigger in action. Let's imagine for a second that we are creating a new social platform. In this platform, we allow users to generate content in the form of posts. These posts can receive comments from other users and other social interactions. Now, we want to store this information, all these posts and comments, in Cosmos DB. And we want to add a new layer on top of our current architecture that analyzes the content that's being generated by our users. The idea behind this demo is to showcase how we can add this analytics layer on top of our existing architecture without actually changing anything in the code of the actual flow that saves the content. So let me show you how it actually works and then we'll see the internals. I'll add a comment to an existing post. And then what's going to happen is that cognitive services will in real time analyze the content I just created and send a notification to the client regarding the cognitive services analysis of the comment I just done to the existing post. I can go to my existing account and check that we are indeed saving this comment as a document in a live Cosmos DB account. I'll switch now to Visual Studio just to show you that you can also use this IDE to work with Azure functions. In my function, I'm using the Cosmos DB trigger as a triggering method. The trigger also has a database name, collection name, and connection string, much like the input and output bindings, but the difference is that it inputs a list of documents. These documents are the ones that were modified or inserted in the collection we are monitoring. The extra attributes in the trigger are meant to configure the collection that the trigger uses to store the leases. The leases are a way to checkpoint the current progress that the trigger is doing over the changes that are happening in the collection. So basically, what this function is doing is it's listening on changes that are happening on a given collection and then receiving all these documents and calling the Cognitive Services API for each of them to analyze the text and obtain a score of sentiment analysis. Now you might recall our demo of the static client and how important it is to maintain all HTTP-based clients as static variables. This function maintains a cognitive analytics client as a static variable and reuses it in all executions. It is especially important in scenarios using the Cosmos DB trigger with collections that can have thousands or even millions of modifications and insertions in a minute. Much like we did with Visual Studio Code, let's set a breakpoint at the start of the function so we can see what happens when a new document is inserted in the collection. Now let's go to our post, and for the sake of the demo, let's not agree so much with the statement. This will insert a new document in the collection. Now the breakpoint will hit. In this case it only contains one document, but if my application had, for example, thousands of insertions or modifications in a minute, this batch could be much bigger. Now let's add a second breakpoint after the cognitive analytics call, and we can see the score that the text analytics service is giving for our comment. We can see that it is not as positive as our first comment, and the last ingredient in this recipe is called Azure SignalR. SignalR is a framework based on top of ASP.NET Core that will allow you to push content using the WebSockets or server-side events protocol to connected clients. And since it's provided by Azure as a service, you don't need to maintain or create any host. You just need to push the content to the SignalR instance and all the connected clients will receive the update. In this practical case, once the Cognitive Analytics API analyzes all the documents, the results will be pushed to the connected clients and the connected clients will render the results in the UI. Obviously this is an educational demo. You probably don't want to render the results of the APIs on the client, but you can use them to provide real-time notifications to our connected users. And since SignalR uses the WebSocket protocol, this is compatible with any mobile client too. So this is great for any real-time scenarios. We can take the data as is being generated in our Cosmos DB accounts and then provide real-time feedback to dashboards or even gaming platforms based on the data that is being saved. After seeing it in action, you might be wondering, but does it actually scale in a real-life scenario where we are having thousands or millions of documents being inserted in our collections. To understand what this trigger is actually doing, we need to first understand a concept called the Cosmos DB change feed. The change feed is present in all Cosmos DB accounts with no extra charge and allows for a synchronic and incremental read on the events that happen in a collection for each partition key range, much like seeing the timeline for that collection. To work with this timeline, you need to implement a checkpointing logic because you need to keep track of the point in time where you are currently reading from the change feed, and also keep in mind that the partition key ranges can dynamically change during the lifetime of your application. Maintaining this logic, plus the ability to scale workload and distribute it evenly among listeners' instances, is no easy feat. That is why we created a Nugget package called the Change Feed Processor that enables you to create your own scalable consumers for the change feed in a pretty easy way, and it takes care for all the checkpointing and load distribution among all your consumer instances. This concept goes hand in hand with functions. Each function acts as a change feed processor, listening on the change feed. As your function scales up or down, it will evenly distribute partition key ranges and load among the existing instances. In the end, all the heavy lifting is done for you, and you just need to take care of the actual code that you want to run on each batch of changes. I hope you have enjoyed this video. You can follow up by installing the Azure Cosmos DB emulator in your local dev environment, or try the Azure Cosmos DB service for free. Finally, here is the main link containing all the source code samples that I've used during this video. And here are the main points of contact that you can use to contact the Azure Cosmos DB team.